Welcome to Standing on the Shoulder of Giants, and this week we're looking at the search for life in the universe. Are we alone? The search for life on other planets is, without a doubt, one of the most compelling and potentially groundbreaking pursuits in all of astronomy. The idea gets at the very heart of our fundamental human curiosity about the universe and our questions about how we got here and whether or not we are alone. Searching for alien life might sound fanciful or unrealistic, but the field of astrobiology is actually dedicated to answering some very rigorous scientific questions. First, we want to understand where we should be looking. In the previous program, we learned about the thousands of exoplanets that have been discovered, but not all will be hospitable to life. Defining the habitability of planets can be complicated, but we need this definition if we are to understand how to direct our searches for life on other worlds. We also need to define what exactly we mean when we talk about life. Even finding signs of tiny microbes or fledgling ecosystems or alien plants on other worlds would be nothing short of groundbreaking. But how can we tell if a faraway planet has bacteria or plankton or trees even? What telltale signatures can we use to search for life? Finally, while finding any life at all would be a monumental event, many astronomers have carefully considered an even more incredible option. What would it mean if we found intelligent life on another planet? This question raises others like, how do we define intelligence? How likely do we think communicating with another world might be? And how can we turn what sounds like a compelling fantasy into a scientific reality? These are the fundamental questions posed in astrobiology and the search for extraterrestrial life, and we'll address all of these during this program. Astrobiology combines astronomy with other fields ranging from biology to chemistry to geology to study life in the universe. Researchers in this field examine other planets as potential biospheres that could be home to extraterrestrial organisms, and most of this potential is focused on what we call habitability. Habitability boils down to one fundamental question: can a planet host liquid water? Earth is our only frame of reference for a habitable planet. But even here we find life forms surviving and thriving in shockingly harsh conditions. We've discovered organisms that breathe sulfur and bacteria that can survive extreme gravity or live half a mile deep in an Antarctic lake. Eyeless creatures live out their entire lives in pitch-dark caves, and microscopic creatures known as tardigrades have even survived exposures to the vacuum of space. But despite all these differences, the only universal need for all living things on Earth is liquid water. Water is therefore seen as a non-negotiable requirement for supporting life. So how can we tell if a planet has liquid water? We have talked in previous programs about using spectroscopy to sort out the light from a star or planet according to its wavelength, and search for the telltale signatures of atoms or molecules that are absorbing light. But we also learned how challenging it is even to find planets around other stars. And since planets don't emit their own light, but merely block or reflect the light of their host stars, studying the chemistry of these dim and distant objects can be incredibly difficult, pushing today's telescopes to their limits. However, we can use what we know about a planet's orbit and host star to define something called the habitable zone. The habitable zone sometimes earns the nickname Goldilocks zone, because it represents a range of distances from a host star where a planet could host water based on its temperature. Too close to the host star and any water on the planet would sublimate into gas. too far and it freezes into ice. But planets that stay at just the right distance from their host star will be able to maintain a surface temperature that allows for liquid water, marking the sweet spot where life, as we understand it, can occur. Of the more than 5,000 exoplanets that we've discovered, only a tiny fraction of them, less than 1%, sit in their host star's habitable zone. But simply being in a water-friendly region doesn't guarantee that a planet could be habitable. The planet needs to be rocky like Earth or Mars, rather than a gas giant like Jupiter or Saturn that simply drifted inward from the icy outer regions of the planetary system where it likely formed. We also need to consider things like the potential atmospheric pressure and geology of the planet, and whether its environment is exposed to hostile radiation thanks to its host star. Between 2005 and 2010, a team of astronomers discovered several exoplanets around the star Gliese 581. One of these planets, about 5.5 times as massive as our own Earth, sat tantalizingly within the star's habitable zone, and with its low mass the planet seemed, at first glance, to be potentially rocky and Earth-like. At only 20 light-years away, it was an immensely exciting candidate for the first exoplanet that might truly be habitable. Unfortunately, further research revealed bad news for any potential life on this planet. It had likely been bombarded with X-ray and ultraviolet light from its host star earlier in its life. Data also showed that the planet could be suffering from a runaway greenhouse effect, with thick clouds of greenhouse gases like carbon dioxide and water vapour trapping heat and driving the surface temperature past the point that would vaporize any liquid water. Finally, the planet is close enough to its small, cold host star that it may have become what's called tidally locked. Like the Moon around Earth, the planet's rotation period and orbital period are the same, meaning that the same face of the planet stays pointed towards its host star at all times. This would wreak havoc on the surface habitability of the exoplanet, roasting one side of it and freezing the other. A planet that, at first glance, seemed wonderfully habitable, thanks to its presence in the habitable zone, turned out instead to be a very poor bet for successfully hosting life. Today, a handful of planets are considered our best candidates for potential habitability. Earth-sized and likely rocky, orbiting host stars that probably haven't blasted the planets with radiation, and far enough from their host to avoid getting tidally locked. Still, even these data aren't enough. Without taking a much closer look at these planets, it's hard to say what they might be like, or what this implies for their surface conditions. Beyond all that, discovering a planet that can host life is quite different from identifying a planet that does not host life. Even if we did find a compelling candidate planet, how could we possibly be sure that there's life on it? Looking for life on other planets could mean searching for signs of any living thing, from microbes to megaflora or fauna. But what are the telltale signs that life might be present on a planet? How can we know, from so many light years away, whether some alien form of bacteria, or shellfish, or dinosaurs might be thriving on the surfaces of planets we can barely even spot? The answer delves into how these creatures impact the planets they're living on, what they leave behind, how they affect their environment, and how all of this might translate into something we can observe. These effects are known as biosignatures, the observable effects of organisms breathing or eating or excreting, changing the land masses or oceans or atmospheres of planets in telltale ways that could alert us to their presence. Vicki Meadows, an astronomer at the University of Washington, leads a group that specializes in habitability and biosignatures by asking an interesting question. What would our own Earth look like as an exoplanet? If an alien astrobiologist trained a powerful telescope on us, what would they see? We can imagine the answer today with a teeming mass of humans on the planet. They might pick up electromagnetic signals thanks to radio and television, or unfortunately detect the chemical signatures of pollution that we pour into our atmosphere. However, humans have only been on Earth for a few 100,000 years, and technology-savvy humans for only a few hundred. What if the alien astrobiologists had observed the Earth 100 million years ago, during the time of the dinosaurs, or even earlier, when life on Earth was dominated by early bacteria? They might have recognized the presence of dinosaurs by detecting signs of, well, we'll call it dinosaur digestion, releasing methane that would show up in Earth's atmosphere. As for bacteria, we know that about 2.5 billion years ago, early life forms known as cyanobacteria were the dominant source of life on Earth. Those first bacteria survived thanks to photosynthesis, using energy from the sun to produce and release oxygen, and they did this so efficiently that we think they fundamentally altered Earth's atmosphere, changing it from oxygen poor to oxygen rich. An enterprising astrobiologist in another planetary system might have been able to spot this effect. Thanks to research from Vicky Meadows' group, astrobiologists here on Earth can now try and search for planets that span a broad range of different evolutionary states when it comes to the life that they might host. Studying exoplanet atmospheres is immensely challenging. We heard earlier about the difficulties of simply taking a spectrum of a planet and studying its atmosphere in the same way that we study stars. However, applying the same corrective methods we use to discover exoplanets can give us at least a glimpse of what these planetary atmospheres might look like. Just a few years after we began discovering exoplanets, Sarah Seeger, an astronomer at MIT, began imagining how we might study these planets' atmospheres. Remember the discovery of Pluto's atmosphere? We observed a background star as Pluto passed in front of it, and noted the initial gradual drop in the star's brightness as Pluto's atmosphere partially blocked it. Sarah Seeger first imagined doing something similar with an exoplanet discovered thanks to the transit method, passing in front of its host star. If that planet has an atmosphere, there should be a brief but precious window of time when the light from the star is passing through that foreground planetary atmosphere. Observations taken at exactly the right point could capture what's called a transmission spectrum. Watching the starlight pass through the planet's atmosphere and measuring the effects of the atmosphere on that light to suss out some atmospheric chemistry. Early observations of transit spectra have shown that it's possible to identify molecules like methane, carbon dioxide and water, all exciting prospects if we're searching for signs of life. Finally, efforts to spot signs of life, or at least former life, have also been happening much closer to home. Right now it looks like our nearest planetary neighbour, Mars, is only home to robots, with rovers roaming its surface to study the red planets in incredible detail. Heroic teams of scientists and NASA engineers have worked for years to keep these rovers running, giving us by far our best and closest look at what life would be like on another planet. Today's missions to Mars are still studying its atmosphere, polar ice caps and geology in the hopes of spotting any signs that life used to exist on the planet. This evidence of long-dead microbes would be an incredible discovery, giving us our first look at what alien life might be like. Research by Seeger and Meadows is still ongoing, driving astrobiologists' efforts to predict and observe the elusive signs that life might present on another world. A continued study of Mars also offers us a potentially compelling close look at alien life that may have existed in past eras. Still, when most of us imagine aliens, we don't picture microbes as exotic as they might be. Anyone who's pondered life on other worlds has imagined what it might mean if the life was like us, if it was intelligent, if it could communicate, and if we could talk back. What does it mean to search for intelligent life on other planets? Where should we even start? How do we know a distant civilization is trying to talk to us, or if there even are any distant civilizations at all? How can we separate science from science fiction when we imagine intelligent alien life? Frank Drake famously tried to tackle this question from a probability standpoint. Drake grew up in Chicago in the 1930s and began studying astronomy in college at Cornell University. While there he attended a lecture by Otto Struve, an eminent astronomer who was, at the time, seen as quite unusual for his vocal belief that extraterrestrial intelligence was real, common, and worth searching for. This was in 1951, years before the space race began. But ideas that might have seemed fanciful to most listeners caught Frank Drake's attention. Drake's early research focused on radio astronomy, studying everything from Jupiter to pulsars. His choice of research wasn't by accident, even if he wasn't focusing on extraterrestrial intelligence at the time. Radio signals had long been seen as a compelling potential means of detecting signals from other worlds. Back in 1924, Mars made its closest pass to Earth in nearly a century, and astronomers encouraged what was called a National Radio Silence Day, encouraging people to cease radio transmissions at regular intervals. The United States Navy Observatory sent a dirigible aloft with a radio receiver attached in the hopes of picking up a Martian message. The research team even had a cryptographer at hand in case translations were needed. This campaign happened before we knew much about Mars, and the years before Karl Jansky first detected radio signals from space in 1931, launching the study of radio astronomy. Still, it set an early standard for trying to hunt for extraterrestrial signals in the radio regime. In 1960, Drake took the opportunity to study two nearby stars at West Virginia's Green Bank Radio Observatory, one sun-like and the other just a bit cooler, in the hopes of spotting signs of life from imagined planets. During the following year, Drake helped organize a small informal conference at the observatory. The group included a Nobel laureate, a member of the U.S. National Academy of Sciences, and a young and up-and-coming researcher named Carl Sagan. In preparation for the conference, Drake assembled what is now famously referred to as the Drake equation. It's a bit different from any other equations you might have seen before. For one, it looks nice and simple, just a series of numbers that we multiply together. The equation is meant to give us a value of n, the number of civilizations in our own galaxy that we could potentially detect. To get that value, we multiply several important numbers. We start with r-star, the average rate at which stars form in our galaxy. We then multiply by the fraction of those stars that have planets, and by how many of those planets can potentially support life. To keep going, we consider what fraction of those planets actually develop life. How many of those developed life forms evolve into intelligent civilizations? How many of those civilizations build technology that releases some signs of their existence into space, and how long those civilizations and technological capabilities last? The Drake equation is also unusual in that we can't yet easily measure most of these numbers, and the scientific implications of the equation change dramatically depending on what numbers you plug in. In this manner, Drake's math is less of a perfect computational equation and more of a statistical exercise or thought experiment quantifying how we should think about extraterrestrial intelligence and how we might evaluate scientific ways of searching for it. The search for extraterrestrial intelligence, commonly abbreviated to SETI, has long struggled to get serious scientific reports and funding. For a time, NASA earmarked funding for SETI, and one project in 1971 funded a report authored by Bernard Oliver and John Billingham that proposed construction of a spectacular 1,500 dish radio array nicknamed Project Cyclops. The array was never built, but the report caught the attention of a young astronomer named Jill Tarter. Tarter had grown up in New York State and expressed an early interest in engineering, which she studied at Cornell University, before continuing on to graduate school in astronomy at the University of California at Berkeley. After reading the Cyclops report, she began working on other SETI radio projects, ultimately dedicating her career to the science of searching for extraterrestrial intelligence. This included spearheading tireless efforts to secure funding for supporting SETI research and building cutting-edge radio observatories. So far, we haven't had much luck with the detecting of signals from intelligent life beyond our own planet. There was a famous WOW signal, however, a signal detected by an Ohio radio telescope in August 15, 1977. The signal lasted 72 seconds and was incredibly bright and resembled a radio transmission far more than any astronomical phenomenon, but it was never picked up again. To date, there's no widely accepted explanation for it. We know what our attempts to communicate with intelligent extraterrestrial life look like. Some have taken the form of directed messages or analog creations travelling at a relative snail's pace. The Voyager 1 and 2 spacecrafts, launched in 1977, carried famous golden records on board. Carl Sagan, who led the NASA committee that assembled the records, described them as some sort of message in a bottle, hurled into the interstellar ocean in the hopes that spacefaring travellers might one day pick it up. The record cover was etched with a diagram explaining how to play it. On the upper left, the cover would pictorially guide the imagined recipient through building a phonograph and stylus, with the stylus illustrated in the position required to play the record from the beginning. Binary numbers explained the rotation rate of the record and how long the record will take to play. On the right, the cover explains how to assemble pictures from the data on the record, which were recorded in binary numerical form. Finally, on the lower left was a map to Earth, showing our position relative to 14 pulsars, the same beacon-like radio-emitting stars discovered by Jocelyn Bell. An extraterrestrial civilization with its own radio telescopes should be able to spot these pulsars, follow the map, and drop by to let us know they'd got our message. The record itself included everything from pictures stored in binary numerical form to recordings of voices and music from civilizations all over Earth. More than 100 pictures showed planets in our solar system, graphical summaries of key scientific concepts, anatomical diagrams and photographs of life on Earth showing everything from natural wonders to supermarkets. The audio included spoken greetings in 55 human languages and sounds of Earth ranging from thunder to rain to whale song. It also includes 90 minutes of music from all over the world, ranging from Congolese folk music to Louis Armstrong to a selection of Igor Stravinsky's Rite of Spring. The record even included an hour-long recording of the brainwaves of Anne Dryham, as she thought about Earth's history, life forms, trials, tribulations, and even the human experience of falling in love. Later she was to go on to marry Carl Sagan. The Voyager spacecrafts don't move quickly. It took them decades just to leave our solar system. But the message they carry is nevertheless headed into the unknown, in the hopes that someone might one day receive it. Other signals for distant civilizations get sent from Earth every day. Radio signals produced here on Earth are now powerful enough to travel out into the universe on their own, spreading outwards in steady waves at the speed of light. One by one these signals are reaching nearby exoplanets and serving as beacons. If there's anyone there and listening, it should be pretty clear that there's some intelligent life here on Earth. It's easy to get skeptical about whether devoting scientific resources to SETI is worth it, and there are plenty of people, even plenty of scientists, who think that extraterrestrial intelligence is simply too rare, too sparse, or too fanciful to be worth much time and money. However, imagining the alternative, the day when we do detect signs of extraterrestrial intelligence, is impossibly compelling, and would without a doubt represent the most astonishing scientific discovery of all time. This ultimate scientific achievement, discovering life elsewhere in the universe, benefits from a long cascade of astronomical discoveries and innovations. Our search for extraterrestrial intelligence depends on our ability to find other habitable worlds, which in turn depends on robust efforts aimed at finding exoplanets. We learned in our previous program that studying exoplanets requires us to understand everything from star and planet formation to general relativity and the possibilities offered by cutting-edge telescope technology. The heroes of astronomy, both today and tomorrow, are constantly pushing forward to pursue new discoveries in all of these areas, testing new theories and making groundbreaking new technological advances that shape our ability to observe and interpret the cosmos. These heroes and astronomical discoveries of tomorrow will be the focus of our next and last program. Well, it's that time again, and time has finally caught up with us. As I said, next week's show will be the last in this series of Standing on the Shoulder of Giants. But never fear, I'll always find something else to talk to you and bore you with. So, until then, everyone stay safe, look after one another. Bye for now.